Okay, hello everyone. I'm a believer of starting things on time. It's 2 o'clock, so let's get started. First, I'd like to acknowledge our sponsor, Lockheed Martin, for this seminar series. My name is Jay Shim. It's my great pleasure to introduce Dr. Jeremy Brown to the audience today. Jeremy graduated from, he got his master's in PhD from University of Michigan.
Go Blue!
And he had a postdoctoral training at UPenn, University of Pennsylvania, before he joined Johns Hopkins University as an assistant professor. A couple of years ago?
Yeah, a couple of years ago.
Yeah. I'm not going to waste any more of your time. Please join me welcoming Dr. Brown.
All right, thank you. Can everyone hear me okay? Okay, cool. Thank you, Jay, for the introduction. So today I'm going to be talking to you a little bit about the work that we're doing in my lab at Hopkins. My background is in the area of haptic feedback. I will spend a few minutes in the talk kind of maybe giving a high-level overview of haptics. I find that this part of my talk is generally not needed as much these days because haptics is becoming, a common term. When I went to grad school back in 2009, I actually did not know what haptics was. The field has grown a lot in the last couple of years. So I'll try to gloss over it because as I've had conversations throughout the day, I've realized that, that you all here are well, let's say, knowledgeable of haptics and kind of the role of haptics. But today I'm going to be talking a little bit about where in my lab, the Haptics and Medical Robotics Laboratory at Hopkins, where we see the role of haptics in particular for telerobotic devices. And I'll talk about a few of the different types of telerobotic devices that we've been working with in our lab, some applications. And then if I get through all the way to the end, maybe some kind of late-breaking stuff that, just kind of came out of the lab. Most of the stuff that I'm going to talk about are, experiments that we've been running and have already collected and analyzed data on, but some things that we, systems that we built that we haven't even yet to collect data on, if I get a chance to at the end. So anyway, let's see, to prime the talk, I'll, kind of start by maybe putting up on the page something that everyone, that most of you here are familiar with, right? It's a task that we do on a daily basis. These tasks require a high level of dexterity in them. It starts, at a very early age. That's actually a picture of my son putting puzzle blocks in a puzzle together. It quickly develops from there into ability to handle objects that have unique properties, right? You think about eggs, which are very brittle. We can pick them up, we can move them around and people to juggle with them, right? And not break them. We do complicated tasks that we don't even necessarily think of as complicated now, like tying your shoes every morning, right? It requires tight control over both your motions and the forces that you produce. You can extrapolate that out in the field of surgery and think about surgeons tying sutures. It's a very similar type of motions or a very similar skill set. We can do tasks that require, let's say high forces. You think about hammering a nail in. You take this, you're swinging this hammer through the air and you're landing on a nail head that's, about yay big in order to get it to drive into the wood. And you're doing it with a lot of force at fast velocities. And then in my, a lot of the work that we do is in the surgical space. So we're talking about, dexterity with, tissue that's very delicate. That if you pull too hard, you rip it, you damage it. You're sometimes trying to cut it on purpose. Sometimes you're trying not to cut it. And so we do dexterity a lot. I'll let's say the reason, and this is kind of going forward, where does that dexterity come from? Well, let's just take a simple example of grabbing this little, in this cartoon, this green ball here, right? If you wanted to pick up a ball, what would you do? Well, you first, think, I want to pick up the ball. And then what happens is a command comes from the brain, down, down the spine, out to the periphery that tells the motor, the muscles to move, to reach out to the ball and to pick it up. All the while, you're generally watching that happen, right? If I wanted to pick up this bottle off the desk, I'm watching it as I go grab it. But also at the same time as you're watching it, you've got this other sensory information that's being passed back to the brain. And that's where my lab focuses on, this blue channel here. And this is our haptic, our afferent sensory information. We like to, at least in the field of haptics, like to break haptics kind of into two subdomains. The first is what we call our cutaneous sensation. And this comes from a number of small mechanoreceptors that are embedded in the surface of the skin that measure things like pressure, vibrations. We've also got sensors that are embedded in the muscles themselves, Golgi tendons, that give us information both about the proprioceptive information, so how our muscles are stretching, right, where our body is at any given time, but also the forces that our muscles are producing. And we like to refer to this as our kinesthetic sense. So we like to, in our field, we break haptics down into kinesthetic and cutaneous. That may be different. I know that in other fields, neuroscience, kinesthesia can be lumped into a lot of different things. Proprioception, they like to sometimes separate out. But this is kind of the, let's say, the model that I run with, and as we talk about the work that we do. So let's go back to these dexterous tasks, and let's take one in particular, very simple one. You may or may not have done this, but just take a match and strike it on the matchbox to light the match. The video I'm going to show you is a very old video, but it's, I hope, very compelling. It's some work done by Roland Johansson a long time ago, where what they were interested in is what role do the tactile cues, or these haptic cues, have in our ability to do dexterous manipulation. So what you're going to see is two videos. The first here is just normally, just a normal case of picking up a match and striking it on the matchbox. Right, pretty simple to do. It's pretty straightforward. Now, this time around, they asked the person to do the same thing, but in between, they apply local anesthesia to the tips of the participant's fingertips. And so let's see what happens this time around. Okay, so a couple of things to take away. One, the participant was still able to actually do the task, right? And that is because he or she was visually watching what was going on, right? And we know that we tend to be very visually dominant. But we saw that it took a very long time, right? The movements were pretty clumsy compared, especially to the first video. My premise for all of this is that this is actually how we operate most telerobots today, that provide visual feedback but no haptic feedback, right? That you can only see when you do your operations, you can't feel, and that lack of touch is what makes the dexterous manipulation abilities really hard. Okay, so let's go back and start talking a little bit more about telerobots. Why do we need telerobots? Well, there may be times, we know that, we use, like I said, back to the original slide, we use our limbs to do a lot of dexterous tasks, but there may be some scenarios where you may not or may not be able to directly interface with the environment in question, right? So you imagine operating at long distances, as is the case of, operating out of space, or let's say the environment that you want to manipulate may be dangerous or harmful, right? Like an IED. It could be, at a different scale. Or in the case of minimally invasive surgery, there are limitations to access, right? You want to be able to operate in a patient's body, but I'm allowing you to only make an incision that's about, the width of a finger. And so how do you get full dexterity inside the abdomen when you can only get to it through the width of a finger, right? Well, in those cases, and then there are also, I should say, scenarios where the body itself is no longer able to do dexterous manipulation because it's been, the body has changed conformation in some way, as is the case of an amputation. And there, you're just trying to do, let's say, activities of daily living, back to the original slide again, things that we normally do all the time, but you don't have a fully functioning limb like your healthy, intact limb is. Well, what we need is some sort of interface, right, that takes the intent or the actions that we want to do and imparts that on the environment on our behalf. We refer to that interface as a teleoperator. Just as exercise in history, the original teleoperators were invented by a researcher by the name of Raymond Gertz, who designed them to basically handle radioactive material back in the 50s and 60s. This is an example of one of his original teleoperators. This is all mechanical, no motors in this one. It's all mechanical drive, cable drive from what we call the master side that the operator is controlling to the slave side of the device, which is being manipulated behind the lead glass window. And so what was really interesting about Gertz's original teleoperators is because they were purely mechanical, there was a one-to-one mapping between what the operator did on the master side of the device and what the slave side did on the environment. But there was also inherent force reflection, right? If you saw in the video, there was a little section where the instrument hit the tabletop. The operator felt that on the other end, right? Because of this pure mechanical transmission between the slave side and the master side of the device. So these devices have inherent haptic feedback. Nowadays, though, Gertz's original teleoperators were, replaced by electromechanical devices, and most teleoperators today really we refer to them as telerobots. And there are a number of telerobots that, work in the same, let's say environments that I mentioned before. In my lab, we like to think of an upper-extremity prosthesis as a telerobot because you are manipulating it from a distance. You're manipulating it more proximal to the body, a distal, the distal hand or limb that's at the end of the device. And the same rules apply as in, traditional telerobots. But in general, when we think about telerobots, it's true that we, with good sensing, we can do good one-to-one mapping between, let's say, what the operator does on the master side of the device and what the slave side of the device does on the environment. And, we do that because we've got great sensors, that we put on these robotic devices. But in order to be able to get that haptic feedback, we need to add a haptic interface to the device, right, that provides this sense of touch information back to the operator because it's not inherently there. The problem, though, is that most of the haptic interfaces that are in existence today are really not that high fidelity. They're not providing a lot of information. They're providing little bits of information here and there. And so my lab is really working on, how do we enrich the fidelity of the haptic feedback that one would receive in a telerobot. So I'm going to stop here with kind of the brief introduction and go into some applications that we've been working in. But maybe let me pause and just make sure there are no questions up until this point.
So one of the advantages of fingertips is they've got a real high nerve density. Are there ideal areas to kind of match that nerve density, or do you wind up having to distribute force over a much broader area of surface if you're trying to give haptic feedback elsewhere on the body? Yeah,
great question. So that is true, right? So the question is, when you look at the density of mechanoreceptors embedded in the fingertips, if you've ever seen like the sensory homunculus, that's where you have the highest density. Also, your tongue, your feet. And so if I wanted to replicate that, where would I do it on the body? You were getting to a point that, if I do it anywhere else on the body, I'm kind of limited because the density is not as high, let's say, on the inside, the volar surface of my forearm. And so what we generally have to do is kind of work within the realm of, let's say, the site wherever we're displaying the information. So oftentimes what you'll see in the haptics field is people will do these perceptual experiments first to try and understand, perceptually how how do certain mechanical stimuli get interpreted on this particular part of the body. And if you look in the literature, there are examples of perceptual tests for the inside of the forearm, the back side of the forearm, the back, all over the body, because our sensitivity actually changes on different parts of the body. What makes haptics somewhat complicated and also interesting is that if you compare it to both vision and audition, it's a very distributed sense, right? Vision and audition, you've only got two sensors. You've got two eyes, two ears, and they're responsible for the entirety of, let's say, sensing in that modality. Haptics is a much more distributed sense. Anywhere you've got skin, you've got a sensor. Anywhere you've got muscle, you've got a sensor. And so it becomes a lot more complicated to think about how you replicate something that is as distributed as our haptic sense. But yeah, great question. We do have to work around the density of, the particular site where we are doing the display of the haptic information. And you'll see that in some of the examples that I showed. Okay, so I'm going to talk about three kind of main examples. One is upper limb prosthetics, then robotic minimally invasive surgery, and then finally just some work that we're doing in understanding just basic haptic perception. How do we understand the world when we feel it? The work that I'm going to start talking about, that I will start with in upper limb prosthetics, is done by my PhD student, Neha Thomas, and a master's student in my lab, Garrett Ung. So if you were to get an amputation today, if you were to have an upper extremity amputation today, you've really got two choices in terms of clinical prostheses that you would be outfitted with. One is the body-powered device. It's been around since the post-Civil War era. It's pretty simple. It's a mechanical device. You wear a shoulder harness that's connected to a cable. That cable connects to the prehensor or the prosthetic hand, and it basically pulling on your shoulder, pulls on the cable that pulls on the hand and causes it to open and close. And it usually has a spring that either holds it open or holds it closed, right? So a purely mechanical device. What people like about it, in addition to just its simplicity, is that it kind of goes back to that original teleoperator that I was telling you about, like the Gertz one. Anything that happens out here, because of the pure mechanical transmission, you feel it in your shoulders. So it has inherent force reflection. But, you know, by and large, the majority of prostheses that you get nowadays are actually, myoelectric or rely on surface electromyography to control, let's say, a robotically driven hand. These devices have advantages in that they can give you, generally higher degrees of freedom. Most body-powered devices are single-degree freedom devices. The downside is that they do not have any haptic feedback. And so, kind of one of the areas that we work in our lab is mainly in the area for myoelectric prostheses. How do we give haptic feedback? So I'm going to talk to you really briefly about a study that we ran in the lab where we were interested in, for myoelectric prostheses, does it really matter what type of haptic feedback I give you if that haptic feedback, if these different types of haptic feedback are giving you the same pieces of information? And the two that we're really interested in comparing our vibration feedback, which is very akin to, the feedback that you get in your phone when it vibrates to let you know somebody's calling you or texting you. This one that we call joint torque feedback, I'll explain that a little bit more when I show you a picture. But suffice it to say, vibration feedback is really eliciting sensations in the cutaneous realm. The joint torque is eliciting sensations in more the kinesthetic realm. So we were interested in, does it matter if I give you a kinesthetic or a cutaneous cue? Do you perform the task the same? And then how does that compare to just the clinical standard myoelectric device without any feedback? So we had, in this particular study, two hypotheses. One is that we thought that, of course, any feedback is better than no feedback. So they will both do better than the case where you don't have any information. And we assumed that joint torque feedback would actually do better than Vibrotactile because the haptic cue that we were providing was grip force. And so we thought force and torque are very synonymous. So if I gave you information encoded in force, you would do a little bit better than if I made you have to interpret that force now as a vibration. Or a change in vibration amplitude, which is what we modulated. Okay, so the devices that we use to run this study, we have what we call our mock prosthesis in the lab. The little hump that you see close to the prehensor is basically because we use able-bodied participants for these studies. So the person makes a fist and puts their hand inside the device, and it basically allows us to test principles of, let's say, prosthetic operation with able-bodied individuals. You'll see that there is a cable running along that prosthesis. That cable then connects to this linear actuator here, and that's where we do the actuation. So instead of, you think about a body-powered device where I talked about using the shoulder to do the driving, we have a linear actuator that pulls on the cable. And between that actuator and the cable is a load cell, and that's where we actually do the measurement of the actual grip force. This exoskeleton here is the one that I was talking about, the joint torque feedback. Basically, this device is it's a capstan-driven actuator that sits at the elbow joint and produces moments or torques at the elbow. And then lastly, for vibration, we use a C2 tactor, which is a common vibrotactile device that's used often in research because you can modulate both the frequency and the amplitude of vibration. Whereas in kind of your traditional cheap little vibrotactile actuators, frequency and amplitude are tied together. Okay, so the study that we did was pretty simple, nothing fancy. It was, if I gave you 3 different objects that roughly looked the same but had different stiffnesses, could you squeeze them and actually be able to identify their stiffness? It sounds pretty trivial, but if you don't have any sense of touch, it's really hard to encode force information with displacement, which is what stiffness is encoded in, right? So the task was pretty simple. You'll see here they couldn't see what was going on, but they would, with the prosthesis, this was all EMG controlled, they would squeeze down on these objects, and these objects all had different stiffnesses, and they were required to report back which stiffness they thought the object was that they were squeezing. I won't go totally through the protocol here. If somebody has more questions about the particular protocol that we use, I can always go back to that. Excuse me. We also did another prior to this, prior to actually doing the experiment. We had another component of the experiment where we actually adjusted the intensities of the different feedbacks, because you don't want the differences in your response to be confounded by the fact that the intensity of one cue was greater than the intensity of the other. So we do this, what we call modality matching step, where you basically, it's a user preferred intensity matching, where I match the intensity of one channel to the intensity of the other. And they use this a lot in multimodality cueing, where you're trying to do both visual, auditory, and haptic cueing. And I can talk about that more in detail if anybody has questions. So just jumping straight to the result, what we found, and the task was done in paired comparison, so you'd get a soft and medium block together, and you were asked to say which one was stiffer. You could get a medium hard block together, and you were asked the same question, which one is stiffer. Same thing with soft and hard. And by and large, what we found is that, for in particular for the soft-hard combination, where the differences in stiffness were the largest, that the both feedback conditions did do better than no feedback. I can talk about why that was not the case for soft, medium, medium, hard a little bit further. Suffice it to say, what we found out on the back end is that participants were using incidental cues to be able to guess. And this is the same thing that amputees do all the time. If an amputee wants to pick up a plastic bottle, they'll squeeze it until they see it deform to know that they've squeezed it hard enough so that it won't slip out of their grasp, right? And so our participants were actually cheating the system in some way, and were using these other incidental cues in order to, the ones that were, let's say, closer together, they were trying to use incidental cues, and that's why the differences, they were relying less on the feedback. But in any case, we found, at least for the soft hard condition, and then for the medium hard condition, vibrotactile feedback did do better than no feedback, but we didn't find any differences between the two feedback modalities. So we found support for our first hypothesis, but not support for the second. So it seems like it doesn't really matter. If I give you force encoded as a torque on your elbow exoskeleton, or if I give you force encoded as a vibration, you interpret both of those pieces of information the same, and you're able to perform the task roughly the same between them.
Yeah, for this, the protocol of how you guys test on individuals, is it in the, are these tests done in the first try or after some training or something? Like
so we do a training period. Great question. We do a training period. If I go back, there is a practice period here. During the practice period, though, they don't get the objects that we use in the actual testing period. So we have different objects of different stiffnesses to get them to understand how the device operates, because most people aren't really used to EMG control when they come into the lab, and so we have to get them up to speed on how you even control the device with EMG, and then we allow them to feel what the different feedback modalities are with different with training objects, but these are not the same ones used in tests. Great question.
Was it considered not allowing them to see the actual objects that they're squeezing, so that they wouldn't be able to see the deformity that occurred when they applied force?
Exactly, right, because we're very visually dominant. And so I've got some other work that I won't be able to talk about today where we've compared vision without vision. And the minute you add vision back in, performance shoots through the roof because we tend to be visually dominant, right? And I can look, I could sit this cup on the table and I could fool you visually into thinking this cup was very, very rigid by exerting a lot of effort and you not seeing this thing deform at all. You would say, wow, that cup must be made of porcelain or something. Instead of if I did this, right? You would say, oh, that's a very compliant cup. And so we tend to rely heavily on vision. And when there's discrepancies between vision and haptics, we tend to defer to our vision. And so what we're interested in, the reason we take vision out is not because we don't expect, there are cases where you don't have vision, right? I can reach in my pocket and pull out a quarter. If I had quarters and pennies in my pocket, I could pull out the quarter and not the penny, right? Without looking at it. Or I can, in the middle of the night, I wake up, I know where the lamp is and I know how to flip it on without actually seeing it, right? But there are, what we're interested in really here is testing what is the efficacy of just the feedback by itself. Great question. Other questions? Okay, so carrying forward, we then decided we then wanted to do a study where we said, okay, so it doesn't really matter what feedback I give you. Feedback is just helpful. How does that feedback compare to, let's say, we've already done it to the case where there is no feedback, but then how does it compare to the intact limb, your healthy limb, right? How close are we getting towards what we consider the gold standard, right? Our natural intact limbs. And what we wanted to do is compare that on two bases. One, just task performance. Again, I'm already preempting you that we're doing this stiffness identification experiment again. But then we also wanted to look at, cognitive effort. How hard do you have to think about this task when you're doing it in either of these cases? And so here we partnered with a colleague of mine, Hassan Ayaz, who's at Drexel University, who does neuroimaging, and I'll talk about the particular neuroimaging modality that we used. But we had two hypotheses. One, adding haptic feedback will result in improved performance, but also lower cognitive load. So we'd see less mental effort doing the task when you added haptic feedback back in. And of course, that the intact, natural, healthy limb is still the gold standard. And so we would see, hopefully, what we were expecting to see is that, the prosthesis without feedback was the worst, the natural limb was the best, and the prosthesis with some feedback was somewhere in the middle there, in both, let's say, along both metrics. So similar setup that we showed you before. The objects look familiar there. The only difference here is that we're using fNIRs, functional near infrared spectroscopy, which measures which basically measures oxygenation of blood in the prefrontal cortex, because that's been shown to be directly tied to cognitive effort. And for the intact hand, because we wanted to get out some force measurements, we have a little piezo-resistive force sensor that we push right on the fingertip to be able to measure the force information from the finger. But the task is pretty similar. It's the same task, squeezing the objects. So it's kind of a carryover of the one before. And basically what we found is that in this case, the hand was pretty much near perfect, right? You could reliably identify these three stiffnesses almost at 100% accuracy with your intact hand. With no feedback, you were right around 70% accuracy. So you were, again, like having, and this is what I talked about with those incidental cues, you're able to use some other information to be able to try and elicit, how much effort you're actually having to put into controlling the prosthesis to get it to close down on the device. All these other cues along the way you pick up to be able to identify things. But then when you add vibrotactile feedback back in, or haptic feedback in general, the performance goes way up. So we did see a difference between all three conditions. And then when we looked at the fNIRs imaging, and I'm only showing you one, the fNIRs imager that we had is a 4-channel. I'm only showing you one of these channels. I think this is right medial. So the one here, not lateral, but in general, what we saw is very similar trends. So lower here is better. Lower here means lower cognitive load, lower oxygenation. So the hand has the lowest, right? Followed by the yellow, which is the vibrotactile, the haptic feedback condition, followed by the no feedback condition. And we found that strongest for this particular, like I said, right medial. We saw evidence of it in some of the other left. This was a right, so the other thing is that participants were doing this on the right-hand side. So you have to take handedness of the task into this. But we did start to see some evidence that, yes, in fact, the cognitive load is lower when you add haptic feedback back in. So you're not having, and so that kind of goes back to these incidental cues that participants were using in the no feedback case. And we purposely did not try to take all of those out because we know that is the case. Amputees listen to the motor of their prosthesis all the time when they're grabbing objects. So we didn't want to rule any of that out. And so we just what we're seeing is that adding the haptic feedback back in does, in fact, lower cognitive effort compared to the no feedback case. And we did it through a neuroimaging modality as opposed to these, like a lot of times when people do cognitive effort, they do like secondary tasks, which can be somewhat hard to do, like count from 100 in threes or something like that. Or do reaction time tests. We wanted something that didn't really affect the primary task itself. Okay. Any questions about that? Because that wraps up the prosthetics part.
What does the negative oxygenation mean?
Yeah, so the short answer is I don't really know 100%. This is, again, the work of my colleague. I'm not going to pretend that I know all that there is about the neuroimaging modalities, but suffice it to say, what you're looking at are just biomarkers. There is no real reference level in these. And so the negative doesn't really mean the same thing in the negative that when I asked the exact same question when I saw the data, I was like, well, it's negative. What does that mean? Like, is it the inverse of, mental effort? And he's like, no, it's not. It's just when you take the baseline, this is what you get, and everything is relative to that baseline. Yeah, but the short answer is I'm not going to pretend to sit up here and give you the physiological meaning of what that is. But suffice it to say, the storyline remains relatively unchanged. Question?
So, I know that a lot of the higher-end feedback is kind of overload gestures. Or in other words, they won't necessarily add more EMG sensors. They'll say, okay, you're squeezing medium, hard, you're using the muscles harder or lighter relative to the total force you squeeze them with.
Mm-hmm.
With those, with the resistance at the elbow, the torque resistance, I know that when you flex one muscle, often it kind of radiates out, and other muscles will flex along with it.
Yeah.
So, would that potentially lead to confusion between intended gesture on the prosthetic side?
Good question. And it brings up something that I didn't mention. This was all done on the contralateral arm. So you wore your EMG on this side, you had the feedback on this arm for that exact reason. Yeah, because if the EMG markers were on the same side that the feedback is on, generally what happens is the belly of the flexors and extensors are right back here, right where you want to put the EMG sensors, and also where the straps from the exoskeleton go on. And so, yeah, you do have that interference. We've done it in the past where you have done it on the ipsilateral side, but you have to be very careful about where you put the, and then do really good filtering around the signals to make sure that the device is actually not causing the device to close. It's actually your intended EMG. Great question. Okay, so I'm going to wrap up here, and I'm going to jump into surgery. This is some work done by my PhD student, Sergio Machaca, as well as an undergraduate BME student, Eric Cow, who's in my lab as well. So, sorry. So up in, for the last, let's say, 30 years, this is what minimally invasive surgery mostly looked like, right? Laparoscopic instruments, which are long, skinny instruments that have pistol grip that you operate through very, very tiny incisions, in addition to an endoscope that produces a screen, produces an image on a two-dimensional screen, a monitor, which you can kind of see in the background there, right? And then prior to that, the kind of origins of surgery was, open access, hands with instruments, forceps. This is the goriest picture, I promise. There's nothing beyond that. You're holding forceps, scalpels, everything directly in your hand, right? So you can see how there's a big difference between directly manipulating tissue with your own hands, right, and then manipulating tissue through these instruments. Well, let's say robotic surgery did, when Da Vinci came out in the early 2000s, it tried to replicate, let's say, the dexterity that you got from, let's say, freehand movement with surgical instruments, along with the better visualization that you got from open surgery, right? So trying to look at, a surgical field on the two-dimensional screen, you lack depth perception. And so what Da Vinci did is bring in endoscopes that actually have two lenses, two cameras, and so you get stereoscopic vision, stereoscopic viewers on the Da Vinci platform, right? So he tried to bring to laparoscopic surgery a lot of the advantages that people had, a lot of the advantages that were available, to open surgery. And this is kind of what if you could collapse the Da Vinci down into two images, there's a master console, it's just a teleoperator, and then there are the slave side instruments that are that operate on the patient. What you would expect is that you would have, good one-to-one mapping between what I do at the master manipulators to the surgical instruments, and you'd also get good haptic feedback. But the reality is the Da Vinci doesn't go that far. It doesn't have haptic feedback. There are a lot of reasons as to why. I won't spend a lot of time talking about that, but suffice it to say, no commercially available robotic device that is FDA approved, and I'm having to caveat this a lot more these days now because there have been some relative advances, don't provide the surgeon with any kind of haptic feedback. So they can't feel anything that's going on in the surgical environment. But it's interesting, though, when you talk to surgeons, they will say things like, I can feel with my eyes. And this kind of goes back to your original question about why do we let vision out? Because the reality is we do learn to interpret the physical world through vision, right? If I put this cup here and I kept pushing it further and further and further, at some point you're like, that thing is going to fall off the table, right? You've not touched it. You don't even know what's inside of it, but you just, based on where it is sitting to the table, just by pure physics that at some point its center of mass is going to go over the edge and it will topple over, right? So we do a really good job at visual estimation of the physical world. And so at first when I would talk to surgeons and they would say this, I'd say, yeah, okay, you can feel with your eyes. But the more and more I started to think about it, the more and more I started to realize it's exactly the same thing that amputees do as well. Like when I talked about amputees squeezing objects until they deform so that they know they've grabbed it, right? It's the same concept. I can't feel it, but if I see it deform, right, I know, or if I watch how it deforms, I know something about its physical properties. And so we then started asking, okay, well, how do you develop this skill, right? How do you learn to quote unquote feel with your eyes? And if you think about any kind of like skill acquisition, right, skill is developed over time. Here we decided to say, let's take this particular skill that we're interested in. We call it haptic visual acuity, right? Your ability to, let's say, recognize information visually and tie it to what you would normally want to feel. And just like any skill, right, it's developed with practice, time and time again, doing the task over and over and over again. What we're interested in is, can we speed that up in any way? Because when you talk to these expert surgeons, they will have done hundreds, if not thousands, of robotic cases, right? And, you know, nowadays for residents coming out of trainee programs, you've got, you know, restrictions on the number of hours, the 80-hour work week. A lot of, you know, surgical training is actually not done in the operating theater anymore because of, you know, malpractice liability concerns. So surgeons are having to practice in more simulated environments. So there, you know, the landscape of surgical training has changed. And there's so many new procedures out that you know, that any one surgeon would want to do, right? So by the time you finish a typical residency program, you may have done a procedure maybe once, maybe twice, right? And so how do we help speed up this process of acquiring the skill so that when surgeons, let's say, finish a residency program, they know how to operate comfortably at a platform like the Da Vinci? So we said, okay, well, when the surgeon sits at the console, they're controlling the manipulators, they see the environment all the time. What if we actually provided them some haptic feedback while they were doing the, let's say, the task? If we provided that haptic feedback, and in this case, we're going to do it through sensory substitution, which basically means we aren't back driving the manipulators themselves, as it would be the case in direct force feedback. You think back to the original Gertz teleoperator, we're going to provide it as a sensory substitute, you know, like vibration or other things on the body. If I gave it to you and you practice enough with it, when I took it away, would it be the case that now your vision has started to adapt into this new kind of vision plus haptics? And so we were interested in, like, does that happen? And I'll, you know, the short story is we have found evidence that that is the case, where we've like given you both vision and haptics, and then we've taken haptics away, and performance stays right where it was when you had the vision plus haptics. And you know, this is after the washout of learning and things like that. What I'm going to talk about a little bit more here is this idea that not necessarily taking the haptics away, but what just happens when you add haptics into the training, you know, into training in general. Does that allow people to improve? So this is kind of the precursor to that. And so what we're interested in is if I give participants, let's say, feedback of the forces that they're producing while they're doing some training task, will they actually change how they do the task compared to, let's say, someone who doesn't have this haptic feedback? The task is simple. It's just this is kind of an elementary training task that most surgeons do. It's called peg transfer. The idea is, you know, in this case, it's you pick up the peg, you move it from, or you pick up this little object, you move it from peg to peg. Underneath the task, though, we have a force sensor that's measuring all the forces of interaction. And then the feedback that we're providing is this little device here. It basically is a servo motor that takes a strap and pulls it on your wrist in proportion to the forces that you're generating. And this is some earlier work done by Stanley and Kuchenbecker that showed that this type of haptic feedback is really good for sending signals related to, let's say, the magnitude of some signal like the force. Okay, so I told you about peg transfer. Forget everything about that because I just remembered the task that we did here is not peg transfer, it's ring roller coaster. Similar, still on top of the force plate, but the idea here is that you're taking a ring and you're moving it along the track, right? So we ran a study where participants wore 2 of these, 1 on each arm, these little squeezing devices. The task was to move the ring from the left side of the track to the right side of the track. We had, 20 participants. We broke them into 2 groups. One group had haptics, the other group didn't, and they had to do 12 trials, and we were looking at both the force and the time it took them to complete the task. And basically what we found, and I apologize, we haven't polished this, these plots up yet. This is like straight out of R. But in general, what we found is that, using linear mixed models and that the feedback group on average had lower forces on this task from beginning to end than the no feedback group. So in general, giving them feedback, they just automatically decided to reduce. And we didn't tell them. We told both groups the same thing. Do the task as efficiently as possible while producing the least amount of force as possible, right? So they both got the same set of instructions. But giving the group with feedback knowledge of the forces that they were producing, they actually produced less force overall in the task. So the next question is, okay, well, what did that, I mean, you produced less force, but that means they were probably more careful, which means it probably slowed them down, right? Because they had to be, you think about playing the game Operation where you're not supposed to touch the walls. You have to go very slow in order to not do that. And what we, by and large, found is that it is true. They were a lot slower than our no feedback group. But if you look at their progression over time, they actually sped up at a much faster rate than the feedback group did. I mean, the no feedback group did. So while they did start out very slow, over time they got used to the feedback and got used to performing the tasks of the feedback, where by the 12th trial, you can say that they're starting to get almost at the same speed as a no feedback group. Now, if we carried this out to 20, I have no idea what would happen. Maybe they would have plateaued. Maybe they would have gotten worse. But at least stopping it, where we stopped at 12, you would say that, yeah, they're starting to get much closer in terms of task completion time to the no feedback group. And the reason that that's important is because when you look in surgical training, time is like the metric that they use for everything, right? Hospital stay is in length of time. Operations is in length of time, right? How long somebody is under anesthesia, it's in length of time. For whatever reason, in the surgical space, skill is really tied to time. So anytime you want to introduce something that tries to improve skill, you have to make sure at the same time, unfortunately I had said time, it's not messing up with the person's ability to do it in an efficient amount of time. And so what we're seeing here is that, yeah, haptic feedback does improve your performance in terms of force, but it also, let's say, reduces the amount of time that it takes. I mean, it doesn't negatively affect overtime once you've learned the amount of time that it takes. That was way too many times. Question?
So is it like one person did with feedback and without feedback?
So this was a between subjects experiment where one group had feedback, the other group didn't, and we randomized the participants into those groups.
Because like if I perform the same task like say 5-6 times, I would be much faster with haptic feedback or without haptic. Would it change? Like if I have feedback once and I have feedback like by the say 10th time, I don't have haptic feedback. Will we be able to justify, okay, with haptic feedback is faster or without haptic feedback? Because I have learned the procedure already multiple times and it's trained in my brain, okay, I need to go in a specific way, a specific time.
So sorry, ask the question one more time because I don't think I got it.
So there are like with haptic feedback and without haptic feedback. But so once I have haptic feedback, I went from point A to point B. But the second time I don't have haptic feedback, or like the 10th time I don't have haptic feedback.
Yep.
Because I have already trained my brain, okay, I have to go through this motion.
Yep.
It already knows like what is the procedure to go from A to B. So it's already been trained.
Yep.
So then if I don't have haptic feedback at the 10th time, would I be faster? Would I be slower?
Yeah, good question. I don't have the data to 100% answer that. I have data, and I could pull it out if we have time, where we did a similar experiment where we had basically 3 phases of the same task, 12 trials blocked into 3, let's say, blockings, where in the beginning you started without haptics, then we added haptics in, and then we took haptics out at the end. And what we found is that people started with some force. The minute we add haptics, their forces dropped. But then when we took haptics away, their forces stayed at that level. It didn't go back up to, let's say, the pre-haptic phase, which kind of goes back to the original hypothesis that what might be happening, and I don't have, let's say, all the evidence that suggests that it is definitely happening, is that when we give you the haptics, you start to recognize things that you may not have paid attention to because you're now feeling it, right? So when you see this little ring that I told you, it's really like an elastic washer. When you see that ring start to stretch, right, and you now feel this thing squeezing on your hand as the ring is stretching, you're starting to tie, oh, this stretching must mean that I'm pulling really hard. So the next time I see this thing stretch, I'm not gonna keep pulling because I know that I'm generating a lot of force, right? So that could be what's happening.
And if you look at it by individual user, say those top 2 orange dots in trial 12, was that always kind of user 7's really slow, so they're going to be?
Some of that is, yeah. So this is without removing any sort of or any kind of outlier removal. This is just the raw data. the story gets even cleaner if we try to take out outliers. And for this case, we decided not to take out any outliers because we tried to say this was representative of the population. And within the population, and this is small sample sizes, we're talking about 10 participants. So we tried not to remove any data. But yeah, in fact, user 12, those 2 red dots are a single subject. Right, so that's one, or not a single subject. It's two different subjects, but 2 participants. And if truth be told, it's those same participants that are tracking high the entire time. They started high and they also ended high. And yeah, that's just the way it is.
Other participants and stuff.
Yeah, and like I said, we try to give everybody the same set of instructions, and it's up to the participant to decide how they want to interpret that, right? We aren't trying to like convince them to do it a certain way. We just give them what the parameters are for doing it. Okay. Really quickly, I'm going to go through just keep an eye on time here, fundamental haptic perception. And then I'll try to, like I said, I want to get to some of the late-breaking stuff that we've done. This is done by my student, Mohit Singala. So we started asking this question. This now goes back to like less application-oriented work, just pure how do we perceive the world. And so we asked this question, if I were to explore the world with 2 hands, do I get a better perception of the world than if I were to explore it with a single hand? So do 2 hands, in this case, perceive stiffness, because that was what the task was. You'll see an underlying theme in our lab. We do a lot of stiffness perception. Do they perceive better than a single hand, right? So just think about it in this context. You have an object. You grab that object, and as you grab that object and explore that object, you develop what we call a percept, or just a percept is just a perception, right? So when I grab this cup, even if I didn't see it, if I had you close your eyes and I put it in your hand, you would say, I'm pretty sure this is a cup. What happens if I do that with my left hand, and then what happens if I do that with my right hand? Is the perception of that cup exactly the same? Or the perception of this object in this case exactly the same? And then likewise, what happens now if I take that same object and I actually explore it with both hands? What happens to the percept that develops, right? Is that percept, essentially, does it take let's take the premise that the hands are different, does the bimanual case tend to favor what happened in the left hand or favor what happened in the right hand? Or is it now some tight integration of the 2? We don't really know. So for this case, we have another little device in our lab. It's just, as you see, it's just a motor with an encoder that has this little hand interface on it. But what it allows us to do is build virtual environments, build virtual objects that we can explore and then we can play around with the parameters with. And by that, what I mean is we build virtual springs all the time. In this case, a rotational spring, the torque is just, some Hooke's law, K times the angular displacement. And so what you're going to see in this video here is, just so you're primed, the person is going to rotate their hand. You're going to see the displacement of the motor as read off the encoder, but then also the torque that the motor is producing. And then in between, you may or may not hear, depending on how loud my computer is, a click. And when that click happens, what the experimenter is doing is changing the value of K. And you'll see them do the same set of displacement, but the torque value is going to look a little bit different. To say that, with the same device, we actually can render different springs of different K values. So you can see that the blue here is about the same. The difference is the red. So those are technically 2 different virtual springs where all we've done is tune this parameter K. And so with the same device, we can give you a whole suite, a whole range of K values, and then start asking questions like, does this K feel different or stiffer than this K? And that's what we do. We actually, what we do is run what's called a psychophysical test, right? Where I basically give you, it's almost like if you ever go get your hearing check and they say, can you hear that beep? Can you hear that beep? Or did you hear that beep in your left ear or your right ear? Same thing. What we're giving is one spring that never changes and one spring that's variable. And we alter, let's say, when you get them. But in one case, what we're doing is moving this spring up and down, keeping this spring constant. And every time we do it, we ask you the question, which spring is stiffer? Is it this spring or is it this spring? And then we may flip them and say, which spring is stiffer? Is it this spring or is it this spring? And what we're doing is estimating what's called the just noticeable difference, which is the minimum difference between those springs, the minimum change in that K value that's needed for you to say, oh, I recognize that this is now a different spring. And so psychophysics is used all over the perceptual world for both visual, auditory perception, but it's the main method that we go about testing perception from a haptics basis. So our experiment here, we basically have duplicate devices. So when we want to do unimanual exploration with the left hand, it's kind of equivalent to what you see kind of on the illustration on the right-hand side. It's like taking a spring and pulling, in this case, rotating a spring that's grounded on one end. The same thing for the right unimanual case. We just changed, it's the right side versus the left side. And then the bimanual, you're basically taking the spring and pulling it like this, right? So think of it as taking a spring and pulling it like this, taking the spring, pulling it like this, or taking the spring and pulling it like this. But it's the same exact spring. And does perception change? This is an example of what one of these psychometric curves looks like when you run a psychophysics test. I'll just kind of explain the high level here. What you're seeing is this is from one of the participants that we had. What you do, on the x-axis, what you're seeing is the range of Ks that we've played around with, right, as we sweep the range of Ks. And then on the left-hand side is the percent correct in terms of responses. When did they accurately say the right object was stiffer? And for J and D, what we look at is the 0.75 mark. That's considered, perceptually from the psychophysics realm, where you say 75% of the time, this is you pick out the right stiffness, that's considered your just noticeable difference. The 50% mark, the 0.5 mark, is called the point of subjective equality, which means that you can't tell the difference between the two. And then there's another threshold where you're talking about your ability to just detect a spring. But suffice it to say, we look at this 0.75 mark, and we look at the K values between the different conditions. And what we found is that in this case, the left hand has a lower J and D. In this case, lower means higher sensitivity, which means the difference between the springs can be smaller for your left hand than for your right hand. And I should say that these were all, with the exception of one participant, right hand dominant, according to like an Edinburgh survey, handedness survey.
Excuse me, did you use the sigmoid models? Could you go back to the previous? Yeah.
Oops, sorry, it disappeared.
Did you use the sigmoid model for this graph, because that's like the common function, or you actually saw that was the
So we
by manual, it doesn't look like a sigmoid.
Yeah, so this is fitting. This is fitting a sigmoid for this particular participant. I mean, what we're showing, the sigmoid function is actually fit to the data. And overall, we take all of the data, and when you do all of the data, it has more, it aligns more with the sigmoid function. But yeah. Mm-hmm. And so what we basically found is that, like I said, the one significant difference that we found is that your left hand is technically more sensitive in this case for this particular type of stimuli than your right hand. And this has been recorded in other cases where even right hand dominant people, your left hand is actually more sensitive in terms of your haptic perception. And what we found is that they weren't different at all between in the bimanual case. When we looked at the bimanual case, we found that the bimanual case tended to align more with the right hand. So even though your left hand is the more sensitive one, your perception tends to favor whatever your right hand thinks, right? So we tend to be, again, these are right hand dominant individuals. They tended to go with their dominant hand in terms of what the dominant hand perceived the spring to be, even though the left hand was actually doing a better job at perception.
So this data set is contradictory to the sensory integration theory.
So this data set is contradictory to the sensory integration theory. So the sensory integration basically says that your bimanual percept is actually better than either your left or your right. And they've shown sensory integration for haptics. They've shown it. I've seen some preliminary papers that have looked at it. But there's also some competing evidence that does what they call sensory selection, where if you look at curvature perception, there's some evidence out there that says what you're doing is selecting one hand or the other. Our data tended to favor more of the sensory selection than the sensory integration. Your bimanual percept tended to be more in line with one of your unimanual percepts than to be better than both of them, if that makes sense. Yeah. And so we're doing some follow-up studies on this now to see why that is the case, where we're changing how you explore the spring where, in the bimanual case, let's say, back to this that I was doing, now I have you hold the spring with two hands, and instead of doing this, you ground one hand and you start doing this, or you do this, or we actually turn one of the motors off so you only get, let's say, force information on one hand, or we only record the displacement information from the other hand. We can kind of change your interaction paradigms a lot and actually see, are you actually paying attention more to the force cues? Are you paying attention to the displacement cues? What's really allowing you to build up this percept of stiffness?
So I wonder if it'll be better to use like two different fingers in one hand rather than two hands, because when you use two hands, there is some complications because of the structure of the brain. Two hemispheres receiving different signals and their communications through corpus callosum. So in terms of the experiment, if you want to prove your hypothesis or disprove, wouldn't it be better to use two fingers in one hand?
So I agree. If we wanted to get at the underlying question of interacting with, let's say, one point of contact or 2 points of contact with an object, but when you look at the world of like telerobotics, you're often interacting with two different limbs, right? So you look at the Da Vinci console, you're sitting on the Da Vinci and you're often manipulating objects with the robot where you are using both of your hands. And so that's why we went
more interested in ecological validity.
Yeah, we were more interested in the practical. Okay, if you have to build percepts when you grab objects, right? How does that affect, let's say, the percepts that you build? But I agree. We've also got some work where it's not exactly what you were talking about. It's the same side, and you're focusing on just, let's say, this versus this. We've also got some work where we did springs. Again, well, I guess that's still, it was in the hands, but it was left versus right. So it's still, you've got the hemisphere problem that you're mentioning too. So yeah, but I agree. If you just wanted to test like your ability to interpret information from a single channel versus, let's call this a dual channel, which one does better, then I would agree that that's probably the right way to do it. Yep. Did you have a question? Okay. So with the time that I have left, which is not much, I'm just going to show you really high level some of the things that we've been working on in the lab. That, like I said, all late breaking stuff that we don't really have true results for just yet. The first is this new prosthesis that we built in the lab, which is, this is the one I talked about. It was kind of like the shadow hand. It's anthropomorphically driven in the sense that there are tendons running anterior and posterior, and there are two motors on the back end of the cuff that are driving the hand. And you can actually see here, this is for a paper that we submitted, just recently got accepted, where we were trying out two different control modalities for this device. It's all EMG driven. And then, we did like the standard box and blocks test, just to kind of test functionality of the device. The reason that we like this device over like your standard DC motor style operation is that by having bi-articulation, you can actually control the impedance of the hand itself, right? So you can make the hand completely rigid or very relaxed and compliant, which is what our limbs naturally do in terms of their manipulation capabilities. And so we were interested in, if you were to give that as a control parameter or a control modality in terms of prosthetic use, does that open up a new paradigm of how you control the world? And we also have an integrated haptic feedback system in this device that provides information about the tensions on each side of the anterior posterior, let's say the tension in the cables. Okay. This next device, what you see in the right-hand corner, this is by my student Guido. I should have mentioned that this is by my student Ethan and Ahim, who's actually a high school student who's spending some time in our lab. This is a student Guido who was a visiting scholar. He came from Politecnico di Milan in Italy and spent some time, about 6 months in the lab doing some research with us. He built, one of the more interesting questions in surgical, when you look at surgical training, a lot of people say that VR training is suitable. Yeah, is as suitable as training in the physical with physical setups, but nobody's ever really tested that. So what we did, if you see here in the bottom video, is built identical training setups in both the VR environment and physical. So this is the VR environment and this exact same thing in the physical environment. And we've been running studies now on motor learning to see, does learning, does performance in these tasks differ based on the VR, whether you're in VR, whether you learn in VR or if you learn in the physical world, and then we transfer and say if you learn in VR and then try it in the physical world, is your performance the same as if you learned in the physical world and then transfer to VR? Preliminary evidence right now says that learning in the physical world transfers to VR better than learning in VR transfers to the physical. Results forthcoming. This last study, this one here, is some work where we're doing now not single modality feedback, but we're interested in combining two different types of feedback in the same for the same task. This task here, and I'll go through the video really quickly, is just a simple grabbing a virtual object. And while you're grabbing the object, unbeknownst to you, the weight of the object starts to change. And so we're trying to basically induce slip. And we want to see how you react to that by giving you both the force that you're squeezing with, as well as we have a Vibrotactile cue that's mapped to the velocity of the object. So if it starts to slip, you actually feel it slip, and then we see whether you react or not. And we're interested in this both. And then, if you squeeze too hard, the object breaks, right? Because we're interested in, tightly confined force control. And then the last one here, we're also trying this with interesting paradigms like EMG. Okay, and then the last setup is just a teleoperator. Back to the original teleoperator, where we've now are interested in both the dynamics of the transmission between the master and slave side. So the green here is just a rigid rod. Red here, we've introduced some mechanical dynamics. You've got a spring and a damper, and then the two motors in the middle create an electromechanical teleoperator. If you tie that with a proportional derivative control loop, you have inherent dynamics and we want to see what happens if you take the same master and slave and environment and change just the transmission between the two. How does that affect the percepts that you develop? Okay, with that, I'll end and just thank my lab who's been doing all the work, and I'll take questions kind of offline now because I know we're running out of time. So thank you.